Alright, in this video we will be talking about springs and resonance, and after watching this video you should have a general understanding of what resonance is, and then be able to use and apply this law called Hooke's law, which is related to springs. So let's get right into it. Resonance is basically a phenomenon where an object emitting a sound wave with a specific frequency will cause another object with the same natural frequency to also vibrate, and this is known as resonance. Okay, so basically, if you're able to sing a note that's high enough, like typically an opera singer, this is the example they use for resonance, an opera singer can sing a certain note and it'll cause glass to shatter in the room, and basically that frequency at which she is singing is the same natural frequency as the crystal or the glass or whatever, and it causes it to start to vibrate and eventually break. Alright, so these are some other examples of resonance. If you ever push someone on a swing, you kind of time the push so that the swing gets bigger and bigger and bigger. Any of you have ever been driving before and a guy pulls up or gal pulls up to you next to you in a different car with their music on so loud that it causes your windows to vibrate? That is resonance. And then, as I mentioned, an opera singer can cause glass to shatter if she's singing or he is singing at the right frequency. So this is an example problem. Let's say you dampen your fingertip and you rub it around the rim of a crystal glass, and it causes the glass to vibrate and produce a musical note. What is that effect due to? Is it due to resonance, refraction, reflection, or refraction? And the answer would be resonance. All right. Basically, if you're able to make a glass make a musical note by rubbing your finger on it, you're causing the glass to vibrate in such a way that it's resonating. Okay, so that's resonance. Hooke's law is dealing with springs, and basically Robert Hooke noticed that the amount a spring is pulled is proportional to the amount of force that the spring pulls back. Okay, and the equation for Hooke's law is written right here. So the force by the spring is equal to a constant, and that's what the K is. A lot of times K is referred to as the spring constant. And then X is the distance that the spring is pulled from equilibrium. So there's a picture of a spring over here, and if I pull this spring, like say, down to this point over here, that would be from this spot up here to down here, that distance would be X, okay, in this formula. Okay, so that's the equation for Hooke's law. It's pretty simple, and what you should kind of notice is there actually is a relationship here where let's say you double the distance that you pull the spring, the force would double. Or let's say you triple the distance that you pull the same spring, the force would triple. All right, so there actually is a relationship, or if you pulled it half the distance, the force would be half. As long as you're talking about the same spring, because if you're having different spring constants going on, then that's not going to be true. But if you're using the same spring and you're doubling the distance or halving the distance or whatever the case may be, there is a relationship that actually exists there. So let's talk a little bit about potential and kinetic energy of springs. Let me change my pen color here so that you guys can actually see it, which is always useful. Let's see here. I guess we can try green today. So let's say you've got a block here, and you have a spring attached to the block, and there's like a little, I don't know, metal box or something attached to it. Okay, and basically right now where this spring is, it is in equilibrium, or it's at rest, or whatever you want to call it. It's not moving. Okay, but let's say I pull this spring back, say to this spot right here. Okay, I pull it back this far away from this resting spot right here. At this point, when you pull it back this far, you would still have no kinetic energy, because the box isn't moving, but you would have a high potential energy, or actually your highest potential energy. Right. And then let's say I let go. Okay, what's going to happen? Well, we know this box is going to move this way, right? And as it flies back this way, it's going to come to the equilibrium point. And at this point right here, it would have no or very little potential energy, but it would have a very high kinetic energy, actually moving the fastest at this point. Okay? And then what would actually happen to this box is it would continue to move this way, and eventually maybe like here, and then it would bounce back that way, and it would keep doing that bouncing back and forth until basically friction took over and stopped it. Okay, but you should notice kind of something similar here. In the previous lesson, I had talked about pendulums and where there was like no potential energy and where there was high kinetic energy. That same relationship actually exists with a spring too, because this is another example of simple harmonic motion actually going on here. Okay, so keep that in mind. If you can kind of get that intuition for what's happening with the spring, it'll help you solve problems. So there actually is a formula to find out the potential energy in a spring, and that relationship does exist based upon the distance the spring is stretched and the force on the spring. Okay, so potential energy of spring is written right here. Potential energy equals 1/2 the spring constant, that's what K is, and then the distance squared. Okay, 1/2 kx squared. And basically that is the equation for the potential energy in a spring. So let's do some example problems using this equation. It says a spring with a spring constant of 4 newtons per meter is compressed by a force of 1.2 newtons. What is the total elastic potential energy stored in this compressed spring? Okay, so as always, I recommend one, drawing a picture. Okay, so if I draw a picture of this, basically I've got a compressed spring here, and to me compressed means it's being squished to the left, like you're squishing this spring to the left, and it's being compressed with a force. So the force on the spring is 1.2 newtons, right? And this spring has a spring constant, or a K, of 4 newtons per meter. And basically what we need to do is we need to find out the potential energy that this spring has. So we want to know about the potential energy. What is that? Okay. So what we got to do is first, we can't just solve for potential energy, because if you remember potential energy, the formula for it is 1/2 kx squared. And the thing is I don't know x, right? And I don't know potential energy. So I can't use this equation quite yet. But I can use Hooke's law, which is force in the spring equals negative kx. And you may say to yourself, what is that negative? That negative is going to be implying direction of which the box is moving relative to where the spring is in its relaxed position. Okay, so this would be in the negative direction because it's going left. If I would have pulled it to the right, it would have been positive. So let's solve this bad boy. My force in the spring is 1.2 newtons. My K is negative 4 newton meters. And my x, we don't know, right? That's what we're trying to find out. And so if I crunch my numbers here, x would equal, let's see here, 0.3 meters. All right. So now that I know x, I can now use this equation up here to solve for the potential energy. And I will do that right now. 1/2 k, which is 4 newton meters, over x, which is 0.3 meters. And if I do that math, I get, and I've got to square this. Almost made a mistake there. Got to square that. And if I do that math, I get a potential energy of 0.18 joules. And that's supposed to be an 8. Let me fix that. Potential energy of 0.18 joules. Okay? So that's kind of the type of problem I could throw at you. It would be something like this. Another problem I could ask could be something like this. An unstretched spring has a length of 10 centimeters. So it's saying basically at equilibrium the spring is 10 centimeters long. When the spring is stretched by a force of 16 newtons, its length is increased to 18 centimeters. What is the spring constant? Okay, so as always, I recommend drawing a picture. And so here's this spring with a box on it. And basically what they're saying has happened is at this point, this would be 10 centimeters from the wall. And someone decided to stretch this spring an extra 8 centimeters to bring it out to 18 centimeters. So my x here is actually going to equal 8 centimeters. And that's something I'm going to write down because that's important. X equals 8 centimeters. Okay? And then it says that to do this, a force on the spring was applied, and that force was 16 newtons. Okay, and so what I want to know is, what is K? That's my question. What is K? So I'm going to be using Hooke's law, which is the force on the spring equals negative Kx. And this negative can actually be dropped because all the spring's going to be doing is just restoring itself back to this equilibrium position. If it was being compressed the other way, then the K would stay. So we're going to drop that negative sign because it's just a directional signal for us. So the force on the spring is 16 newtons. And K, we don't know, so that's a question. And then X is 8 centimeters. And so basically just bring 8 over here, and I find out that K equals 2 newtons per centimeter. And that would be my answer. All right, so we'll do some more problems with these, but that takes care of this video, and I will see you guys next time.